Okie dokie. So we are in the home stretch. One last topic to talk about, and that is systems of differential equations. Now, systems of differential equations are going to come about in the real world anytime you have two quantities that are related to each other, so that the rate of change in them, the rate of change in one of them, depends on multiple. So a really good example of a situation like this would be like a predator-prey kind of relationship. So since we were just talking about being out on the ocean, let's talk about something like maybe orcas and seals, because orcas like eating seals if they can get them, right? So think about the populations and how they're going to be affecting each other. So if we were looking at, say, the rate of change in the seal population, obviously it's going to depend on how many seals are there. That's kind of a no-brainer, right? But it's also going to depend on how many orcas are swimming around, because if there are way more orcas, they're going to eat more of the seals and there's going to be a die-off, right? So if we are going to say, let's say X is the number of seals, then X prime depends on both X and Y, the number of orca. But we'd also see that the number of orca is going to depend on both as well, right? Again, clearly Y prime is going to depend on Y. Different number of orca, we're going to have a different rate of change in that population. But it's also going to depend on the seals because they need the seals for food. If the seals start dying off, then the orcas start going hungry, they start dying off, and so on. So I know that's kind of a real simplistic kind of view, but the predator-prey relationship is a great example of where we'll get a system of differential equations. Now, I know not a single one of you is thinking about being a wildlife biologist. However, we can find all kinds of things where this comes about. If you want more of a physics example, if you go back to what I was doing in grad school, I was dealing with systems of differential equations when I was looking at fluid dynamics. And again, you can kind of see how that's going to play about, right? Like if we're going to talk about just real simplistic again, the water and say the tidal channel. Well, the water flow depends on the tidal channel, and the tidal channel depends on the water flow, and so on and so forth. So they're all over the place. So what we're going to do is we're going to look at really simple case. We're going to start with just linear. Okay, so we're going to have linear systems, and we're going to be dealing with ones with constant coefficients. Obviously, you can go crazier, but that's going to require way more than we would have talked about at this level of class anyway. So let me go ahead and go to the whiteboard and show you what I'm talking about. All right, so for example, let's say we have something like this. We have X prime, it's going to equal X plus Y. And then Y prime is going to equal 4X plus Y. So this is what we're talking about when we talk about a linear system of differential equations. So you could have as many of these as you want. X prime, Y prime, Z prime, T prime. You could also have where some of these are double primes and it's related to derivatives and all that. But for linear first order, these are first order, linear, and again, we're going to go with constant coefficients. All right, so the question is, how do we find solutions? Well, the first thing we're going to do is we're going to turn these into matrix equations. Because if they're matrix equations, they're going to be a little bit easier to solve because we can use inverses and whatnot. So notice that if I were to make a matrix out of this, I've got X prime, Y prime is equal to 1, 1, 4, 1 times XY. And this last vector holds my solutions. And so in fact, I'm just going to call that V and realize that what we're doing is we're solving for V. if we get V, that's going to hold the solution. Well, that makes this first matrix V prime. And then we can call that other one A, the coefficient matrix, like we usually do. All right. Quit making fun of me on another window.
Making fun of myself.
All right. So V prime equals AV. So this is really what we're solving for. All right. So what kind of form can V take on? Well, here's what we're going to do. Let's make the same kind of guess that we've always made, that these X's and Y's are exponential. They're some sort of a e to the whatever, right? And then in terms of what kind of form we might have on them or out front, you know, whatever. But let's just say that it's some sort of an e to the RT. So like always, let's assume a form that V is equal to R times e to the t, or not, sorry, R times, some sort of e to the RT. But it can't just be e to the RT, because this is a vector, right? So let's just go with some generic vector times it. So we'll say that it's actually like the vector C times e to the RT. And let's see what this is going to force our R to be. All right, well, V prime then, this is going to be R times that C, e to the RT. And let's put those back into this equation. So we're going to have R times C e to the RT is equal to A times C e to the RT. So I'm going to go ahead and move things over to one side. We get 0 is equal to AC e to the RT minus R C e to the RT. I'm dropping the vector things off of the C, but just remember that's a vector. And what I want to do now is actually factor out. And if I factor out, I can factor out C e to the RT. You get C e to the RT times A minus, and this is going to be R times I. And we need to put that I there because this still needs to be a matrix that we can add to this. And so, of course, this has to equal 0. Now, it's usually at about this point, you guys go, oh, I recognize that. Where have you seen this before? Anybody recognize that?
Yeah. Isn't that similar to the PERT formula?
Little bit. I mean, the PERT bit, that's just because I'm assuming it's an exponential form. But really the part that I'm trying to key you guys in on is the A minus RI. What if we changed alphabet? Instead of an English letter, we put a Greek letter in there. Maybe specifically a lambda. Do you remember A minus lambda?
Eigenvalues. Eigenvalues.
Okay, so now all of a sudden I saw it on your faces. Yeah, this is eigenvalues. So if we're looking for something that's going to make this 0, because C is not going to equal 0. right? Remember, that's just some multiple on this e to the rt is some multiple vector. We don't want the 0 vector because that's just the trivial solution. So we won't let c equal 0. E to the rt, by definition, can't be 0. So it leaves only a minus ri to equal 0. And those are the eigenvalues. So this guy r, it's an eigenvalue of a. All right, so when we go and want to find solutions to this, to the system, we have to find the eigenvalues of the matrix, because those are going to be the exponential, or the powers on those exponential pieces. Okay, even better, this guy C, this is a corresponding eigenvector. So that vector that we're multiplying on the e to the rt, that's going to be the corresponding eigenvector to that eigenvalue. So in addition to the uses of eigenvectors you saw before, here's another one. All right, so the first thing you're going to want to do anytime you have one of these is start with finding eigenvectors and eigenvalues. So let's go back to that example that I'd already put up, where we had x prime was equal to x plus y, and y prime was 4x plus y. So we'll make our matrix A, which was 1, 1, 4, 1. And now we want to find eigenvalues. So we'll make the A minus lambda I. I'm going to write it as an R, but R lambda doesn't really matter. So A minus R times I is going to be 1 minus R times 1, or with 1, and then 4, and then a 1 minus R again. All right, so do you remember how to find eigenvalues?
Take the determinant of it and factor for R and solve for R, essentially.
Okay, so you take the determinant and you set it equal to 0, and then you solve for R. So this goes back to the TFAE list. I know we kind of talked about that last time. And was it you, JP, who's like, I can't remember the TFAE list. It's either you or Wes. But this is one of those where this is going to come in handy. We want to find out where this equals 0. That's where the determinant is equal to 0, because we can't have, well, we need to have a dependent system. So we're looking for where the determinant equals 0. So the determinant of this guy is going to be 1 minus R times 1 minus R minus 4. The 2 by 2 case, you can just do the cross multiply, and we'll set that equal to 0. So this gives us R squared minus 2R minus 3 equals 0. And so the two R values that we're going to find, well, let me go ahead and factor it. It's R minus 3 times R plus 1. And so for this one, I already have a couple of eigenvalues. I've got R equals 3 and R equals -1. All right, but we're only halfway there. Eigenvalues are great, but without an eigenvector, they're not useful here. So again, quiz for class. How much do you remember? How do you find eigenvectors?
You plug in.
You plug in one of them for
So you plug in the eigenvalues,
and then find the what's it called?
Null.
Not
the nullity. Wait, what was it?
No, it's the null space, the null space of it, right?
It's the
Or-
basis. Yep, the
yeah.
basis of the null space.
Yeah.
Yep. Now you guys are dancing around. You're kind of remembering. So
Close.
yeah, we need to find a basis for the null space. So what we'll do is we'll plug in our R's. So for the first one, when we plug in R equals 3 into the A minus Ri, we're going to get -2, 1, and then 4, -2. So what you can do is actually put that into row echelon form. And then that can help you figure out what the basis vector should be. So I'm going to go ahead and just clear that bottom row. Right, if I take the top row times 2 and add it to the bottom. So now let's build what the eigenvector looks like. So in terms of the first, I can have any number I want. It's a free choice. I'm going to pick 1. But if that equals 1, then I'm forced to have a specific value down here to get 0 when I multiply. And what's it going to be?
Zero, right?
Not 0. Like, think about setting it up here and doing the multiply. I'm going to get -2. To get 0, you need to add 2. So since that's a 1, this requires it to be a value of 2. So there is an eigenvector for that eigenvalue. And it's important to realize that that's just one of many, because any scalar multiple of that works. But this is a basis for that eigenspace. All right, so there's the corresponding eigenvector. So then we're going to do the same thing with r equals -1. If I plug that in, I get 2, 1, 4, 2. I can do a similar deal here to reduce it down. Again, I have free choice on the first, so I'll go ahead and just call that 1. But that's going to force the other to be -2. All right, so let's see what the solution then looks like. So what we're finding, this is the fundamental set. It's the fundamental set of solutions. And in this case, this is what it's going to look like. I'm not going to write it as y equals. I'm going to write it as v equals, because remember I'm looking for a v vector. But you can call it whatever you want. But I'm not calling it y because x and y were my variables. Okay, so here's what you do. You take the vector, the eigenvector you just found, and you multiply that by e to the rt, where r was the eigenvalue. So r was 3, so I'm going to have 1/2 e to the 3t. So that's one of my fundamental set. The other of my fundamental set is 1 - 2 times e to the -t. So that's how we're going to build these. You're going to take your eigenvalues, put them in as your exponents, and your eigenvectors are the multiples on them. So there's our fundamental set. But if I want to catch all possibilities, I now have to put on my C1 and C2. So think about this piece, and these pieces. those are our y1 and y2. I guess in this case, we call them v1 and v2. But once we find them, we go ahead and we multiply by arbitrary constants to get our solution. So this would be the solution written in kind of the matrix equation form. But if you wanted to separate it out and write what are x and y, we would get x is equal to c1 e to the 3t plus c2 e to the minus t. Just the first components when we multiply out. The y's, we're going to get 2 c1 e to the 3t minus 2 c2 e to the minus t. So we still have two arbitrary constants. But what's a little bit different now, but shouldn't be surprising, is that choosing the arbitrary constants for one of them determines the constants for the other. They're not independent of each other anymore. But like I said, that shouldn't be surprising because x and y are dependent on each other. How they change matters, how they each change matter. All right, so that's our general process. That's what we're going to do. We're going to find eigenvalues, the corresponding eigenvectors, and then put them together. We usually write them like I wrote down here at the bottom. Write them as a sum of vectors instead of the x and y individually. Sometimes you'll see it as one big matrix, but in general, this is the process. All right, so let's try another one. Let's go to a 3x3 system, just to kind of remind you how to do those. All right, so let's say we've got this, that x prime is equal to y plus z. We'll have y prime is equal to x plus z, and z prime is equal to x plus y. So whatever kind of weird relationship we've got here, the rate of change in one of them depends on the other two, the sum of the other two. All right, so let's basically make A and find their eigenvalues. So A, in this case, is going to look like 0, 1, 1, 1, 0, 1, 1, 1, 0. So really, let's just get this into RREF, because then that will help us figure out what the eigenvectors look like, or the eigenspaces, I should say. So if we do a little RREF, we'll take that 1, 0, 1, bring that up to the top. If I take this away from that one, so I just do -1 plus this to this plus that, I'm going to get 1 minus 1, which then is going to reduce that second row to a 0, 0, 1. And then the other guy, 0, 1, 1, is going to be able to cancel out. And so what we end up with is going to look like this. It's going to be, oh, what am I doing? I don't know why I'm going into row echelon form just yet. I need to do A minus lambda I first. Okay, so A minus lambda I is minus lambda 1, 1, 1 minus lambda 1, 1, 1 minus lambda. There we go. And so now let's find lambda. I jumped ahead a step, right? I was trying to find eigenvectors, but I hadn't actually found the eigenvalues yet. All right, so if we create our polynomial, we're going to get minus lambda cubed. That's from those. We're going to get a +1 and another +1, so +2. And then we're going to subtract a negative lambda and another negative lambda and a third negative lambda. That's going to be +3 lambda. So that's its determinant. We'll set that equal to 0. All right, so this one might be a little bit tricky to do by hand, but of course you can use, your favorite technology to solve this. But you're going to get that lambda is equal to 1 is one of them. You're going to get lambda equals 2 is another. And the third one you're going to get is lambda equals -1. All right, so now let's plug those in and see what that does for us. So let's start with lambda equals 1. If lambda equals 1, we now have -1, 1, 1, 1 minus 1, 1, and 1, 1 minus 1. Okay, now let's go to REF. All right, so when I add these guys together, that's going to give me 0, 0, 2, which will reduce to 0, 0, 1, which will clear all the rest. And then the remaining bits are going to get canceled. So now we need an eigenvector for this guy. So like before, we can choose C1 or the first one to be whatever we want. So how about we just go with 1? But if that's 1, it forces the second one to be 1. So that when I multiply, I actually get 0. And then what's the value of the third coordinate going to be?
The third.
Isn't that just going to be 0? Oh.
Yeah, that would just be 0.
0. Yeah, because the bottom line is just straight up 0, so you can't really do much with that.
Exactly. All right, so there's that guy. Okay, so let's go to lambda equals 2. And I apologize because I don't have enough space if I want to keep this matrix, which I definitely do. So lambda equals 2, same deal as before, right? That'll give us a -2, 1, 1, a 1, -2, 1, and a 1, 1, -2. Again, you can go ahead and get this into RREF. Doing so, you get 2, -1, 1, 0, 1, -1, and 0, 0, 0. And so if you go through the process, you'll find that your eigenvector here is 1, 1, 1. That should have been a minus one. I apologize. All right, so that one gives us 1, 1, 1. So then lastly, let's put in lambda minus 1. All right, so when we put in a lambda of minus 1, that turns this matrix into a matrix of all ones. And that sucker is going to reduce down to 1, 1, 1, and then 2 rows of zeros. All right, now this is where it gets interesting, because we actually have more than one free choice. So I don't know if you remember this, but in a situation like this one, we can actually pick the first coordinate to be whatever we want. Okay, but I'm not going to call it 1. I'm going to call it, how about, we'll call it, say, C1. No, let's not use C. We use C all the time. T. Okay, so I can pick anything I want for the first coordinate. But I also get to pick whatever I want for the second coordinate. But once those two are fixed, I know what the third coordinate has to be. It's going to have to be negative T1 minus T2. That's the only way that when I multiply by 1, 1, 1, I'm going to get 0. So what I have to do is split this up. I have to split it up into 2 vectors. The one that holds the T1s and the one that holds the T2s. Because then I can factor those out. And since T1 and T2 are arbitrary choices, those are like my arbitrary C's, this is one where I actually get 2 eigenvectors. Sometimes that happens. Now, this tells me that I did something wrong, by the way, because somehow along this, we found 4 different eigenvectors, and we only should have found 3.
Because it matches the, it can only match the rank of the space, right?
Yeah, the dimension of the space tells you everything. So we know that we can only have 3. Let me go back and look. So that polynomial was what? Minus lambda cubed plus 2 plus 3 lambda. So what I'm thinking is maybe one of the lambdas isn't actually an eigenvector or eigenvalue. So let's see, minus 1. That makes this negative 1. Negative, negative 1 is plus 1. Plus 2 is 3 minus 3. That's good. 2. Negative 8 plus 2 plus 6. That's 0. 1. Negative 1 plus 2 plus 3 is not 0. Okay, so I apologize for you watching at home. I apologize. Lambda equals 1 was not an eigenvalue. So whatever that first vector we found was, disregard it. Sorry, my bad. Lo siento. All right. So here's how this plays out then. So we just found these two eigenvectors for lambda equals -1. So that means in our solution, there are actually going to be two pieces that have e to the minus t. We're going to have v equals, so do c1, we have a c1, times 1, 0, -1 times e to the negative t. So remember, this was an eigenvalue of -1. So I have e to the minus t times that. We're then going to have plus c2 times 0, 1, -1 e to the minus t. Because that's the some scalar multiple of this guy, also times e to the minus t. And then the last one, and I really think my memory serves it was 1, 1, 1, and that'll be times e to the 2t to go with that lambda of 2. So as long as you can find the eigenvalues and their corresponding eigenvectors, we're good to go. So this is the only place in this class where knowing linear algebra is pretty much needed. You know, we've seen a lot of places where it was useful, kind of assisted us, but this time, no, we definitely need it in order to get this. All right, so there you go. But you probably know what's coming. What happened last time when we went with the, let's just assume a form? It was a long time ago. But...
It won't always be in that form, or?
Okay, so with this one, with the constant coefficients, it'll always be some sort of an e to the RT. Think back when we did e to the RT before. There were a couple of other cases we had to worry about. What happens when R is repeated? What happens if R is complex? Right? Well, what if, in this case then, the lambda is repeated, or the lambda is complex, right? So we have to start worrying about those as well. Now, in this example, you notice that we did have a repeated lambda. That -1, it actually led to two different pieces, right? But sometimes we have an issue with eigenvectors being repeated. It's the eigenvectors that are the problem. If we don't have enough eigenvectors, we're going to run into an issue. So that's where the repeated thing comes into play. But I'm not going to go into that. I want to go into the, what if it's complex? What if we get an eigenvector, or an eigenvalue, I apologize, an eigenvalue that's got a complex number? All right. Well, let's actually just start with an example of a matrix that would do that. And then we'll talk about how we deal with it. All right. So here's a nice simple one for you. Let's say that we've got x prime equals -x plus 2y, and y prime equals -2x minus y. So we make our matrix. We make our A minus lambda I. We go and we find its determinant. Okay, well, well, it's going to be minus 1 minus lambda quantity squared plus 4. And I'm not even going to multiply it all out because this is already in a completed to the square form. So I can actually move that 4 over and now take a square root. And you can see the i's pop up. So we get that lambda is equal to -1 plus or minus 2i. So I'm curious, I think I know the answer. When you guys were in linear algebra, did you ever find eigenvalues with complex numbers?
Yeah, we did.
Okay. Yeah, Larry's usually pretty good about doing that because he knows you're going to need to in the future. But you probably remember that the process is the same. You still plug in those lambdas and see what happens. So when we do say -1 plus 2i, that matrix, if I do -1 minus this, the ones cancel, and I'm left with -2i, 2, and then -2, -2i. And so what the corresponding eigenvector for that's going to be is 1 and I. Right? I can pick whatever I want for the first one, so I'll pick 1. So when I multiply that, gives me a -2i. I have to cancel that with a +2i, so there's my 2. You'll see that it works down here as well. But then again, do the same thing with the -1 minus 2i. And this becomes 2i, 2, -2, 2i. And we get something similar. We get 1 and -i. So far, no big deal, right? I mean, we're doing exactly what we did before. And if we continued that process, you would get something that looks like this. So we've got our V equals C1 times 1i times e to the -1 plus 2i times t plus C2 times 1 minus I e to the -1 minus 2i t. So we're really just following the same process that we did before. All right, but we don't like complex numbers, right? So what we really want to do is get rid of all those i's, but we're going to play the same trick we did before. What did we do before when we had i's as exponents?
Didn't we use Euler's formula to take care of it?
That's exactly it. Use Euler's formula. Do the e to the -1t times e to the 2it. Use your Euler's formula. You'll get a sine and a cosine, a real and a complex, and yada, yada, yada. So let me just sort of get to the end of the story. What we would find is that we get this is our real and this is our complex part. So V would equal e to the lambda t. Let me actually, you know what I'll do? Let me do it just generically, and then we'll apply it to this one specifically. So in general, what you're going to get, your vector, there's going to be an e to the lambda t times, let me name the Eigen Vectors. It's getting way too confusing. Hold on a second. Let me give you what this one will look like, and then we'll talk about the in general. Okay, so if you go through all the work, all the heartache, what we end up finding is we get a cosine t, a minus sine t, times e to the minus 2t, or sorry, minus t. And then this is going to be added to sine t cosine t times e to the minus t times I. So this is the piece that you actually get for the 1 plus, or the first one, the 1i, gives you this. The 1 minus I, because it's a complex conjugate, gives you exactly the same, but with a sign difference, a plus or minus sign difference. And so here are the two pieces that are dealing with this guy right here. And I lied. This is a cosine of 2t, a sine of 2t. Now, here's what I want you to notice. When we did it before and we got a complex number, the real part went in the exponent. The imaginary part led to trig, sine and cosine, and with the two t's, right? With whatever that number was. So we're having the same thing kind of fall out. It's just there's more of it now because of the fact that it's a system. Okay, so let's generalize this. Let's go nice and generic so you can see what the process is. So first of all, hopefully you remember this from the linear algebra, is that when you get a complex eigenvalue, they come in pairs. They're complex conjugates of each other. So kind of like this one, we saw we got a -1 plus 2i, and then we had a -1 minus 2i. So they always come as complex conjugates. All right, so that's good to know. So what we can then do is if we think of those conjugate things as like an a or a lambda plus mu I, the plus or minus doesn't matter at all. Okay, so we're going to have lambda equals, no, let's do it this way. R is equal to lambda plus or minus mu I. So in that case, then, what we're always going to get in terms of our solution space is something that's going to look like this. You're going to get your V equals e to the lambda t, so C1, e to the lambda t times I'll explain where these vectors come from in a second. We're going to get A cosine of mu t minus B sine of mu t. So A and B are vectors, and like I said, I'll tell you what they are in a second. So that's what V is going to, or that plus C2 e to the lambda t. And in this case, we're going to get A sine of mu t plus B cosine of mu t. So the lambda and the mu should make sense where they come from, because it's the same thing we saw a month and a half ago or whenever we saw that. But now what these A and B are, those come from the eigenvectors, right? So not only do complex eigenvalues come in pairs, so do their eigenvectors. So that means we can represent the eigenvector as a vector A plus or minus some vector B times I. And that's what these A and B are. They're the real, A is the real part of the eigenvector, and B is the imaginary part of the eigenvectors. So, similar. It's definitely similar, but it's a little bit more complicated because of that, the fact that it's a system. So let's go back to that one that we just did. And now that I kind of showed it to you generically, let's see what this looks like. So I don't think I pointed out that the eigenvalues and eigenvectors were conjugates of each other, but let's just kind of go back and look at that. So the one we did before, we saw that the first eigenvector was -1 plus 2i. And the second one was -1 minus 2i. The corresponding eigenvalues, or sorry, eigenvectors were 1i, and the other one was 1 minus I. So again, notice that these two eigenvalues are complex conjugates, and the eigenvectors are made up of the complex conjugates. So here's how we're going to break this into all the different pieces. Think of this as real plus imaginary. So this would be the real part is 1, 0. The imaginary is 0, 1 times I. So I'm just taking the coefficients on the real parts, putting them here, coefficients on the imaginary parts and putting them there. For the other one, the only difference is there'd be the minus. So those are your A plus BI and your A minus BI. So in order to put stuff into this formula, here are what all the different pieces are. Lambda is -1. Is the real part of the eigenvalue. Mu is 2. That was the complex part of the eigenvalue. A is going to be the vector 1, 0. Because that's the real part of the eigenvector. And then B is 0, 1. Because that's the imaginary part of the eigenvectors. So that's how you can create all the different things that go into your solution now. But that's what it looks like. So this would be a situation where you end up getting things that are related to each other, and They lead to some sort of a sign, oscillation. And this is like when I first talked about predator-prey models, tend to be like this. They tend to be sinusoidal. You get a peak in the predator population, causes a dip in the prey population, which then leads to a dip in the predator population, which makes the prey population go up. Now there's more food, so predators go up. And you just cycle, 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 cycle. Now in that situation, you should get a lambda of 0 so that there is no decrease due to that or change due to that. But that lambda can cause this to die off. Like in the fact, in this case, since lambda is negative, these things are going to die off as we go far off into the future. If lambda is positive, they continue to grow. So you can get all kinds of stuff happening, but when you get complex eigenvectors and values, they lead to sinusoidal relationships, just like before. All right, so there's your process. That's kind of how we go about doing these things. All right, any questions on that one?
Okay, so I'm going to turn back to this screen for a moment. Okay, so really we're doing the same thing. We're just turning it up a bit because of the fact that we're looking at systems, right? Anyway, so I think with that, I'm going to pause for today.